Thanks a lot. So welcome everyone. I want to acknowledge my team shown here on the slide, my collaborators, students, and postdocs, and my funding. I particularly want to call out the Stanford AI for Health support, particularly Anthem has supported this research. And I want to give a high-level view of actually a number of projects supported by the various funding sources. I'll be talking about, first of all, motivations for AI in medical imaging, just for those who aren't already familiar with that, and highlight some of the applications we're working on in this space. And I also want to focus on some of the challenges, because there's a lot of hype around the applications in medical AI. And I want to talk about some of the technical approaches we're taking to those challenges. So, I'm also a radiologist, and radiologists are confronted with more and more images every year. This is showing a slide. Each row is a different CT study on a patient, and on the left is from 2001, and on the right, 2018, and in green is highlighting the number of images per CT study. And you can see it's almost a tenfold increase in the number of images, and all those need to be reviewed by radiologists. So there is a flood of imaging data, and this is exceeding human capacity to process all this information. So that is screaming for the need of computers to help manage all that flow, that rapid influx of data. Second major challenge that motivates AI is variation in clinical practice. You might have heard the term, if you've been told you have a particular disease or you should have a particular treatment, you should get a second opinion. Second opinion just means there's variation in practice. Ideally, we should just have one opinion, one answer. This was a study of 127 radiologists who were interpreting mammograms. The diagnosis, benign or malignant, was known. And this is ROC space, so we have sensitivity versus specificity, and each point on this graph is a radiologist's performance in that space. And ideally, they'd be in the upper left-hand corner, perfect sensitivity and specificity, but it looks like a shotgun was shot at this graph. There's actually 3 radiologists who had zero sensitivity, didn't detect any cancers, and you don't want to see them. Certainly want a second opinion in those cases. But this is a graphical illustration of variation in practice, and the belief is, well, if computers could be a second opinion or help the clinician who's really overwhelmed with images and needing to get through their stay to be alerted to problematic cases, that would improve the quality of practice, would reduce this variation, kind of move everyone up to that left-hand corner of the screen. And you've probably seen in the press a lot of articles and press pieces coming out about how AI is competing with radiologist performance, approaching radiologist performance. Well, a few people have notably said radiologists will be out of business, but most maturing thought is recognizing that there's going to be particular focused applications where this is really a good fit to help radiology interpretation and practice, and not so much be focused on replacing everything a radiologist does, because there's actually a lot of complexity to the full scope of what radiologists do. But in certain tasks like detection and mammography and diagnosis of benign versus malignant, that's a case where there's clearly a potential role. The critical information that needs to be brought to bear in any kind of a medical task is more than just images, though. Although I'll be focusing on images, I'm also going to be talking about text. At the end of the day, patients have a lot of data about them that need to be analyzed by clinicians when making an evaluation or a treatment decision. And so it's actually a combination of images and text and structured data like genomics. You heard about that earlier from you and Ashley. But there's a difference between the structured information that's parsable by a machine, like lab values, demographics, and genetic data, versus image and text, which are unstructured objects and need some sort of a formal representation. So everyone in the room probably is familiar with the representation of images in a deep learning paradigm, where it's a pretty simple representation. You just put the whole image in, and you train a complicated multi-layer network to produce an output, like is there a mass or is it benign or malignant, which kind of mimics how the visual system and other hierarchical structures in the brain work. And the representation of an image is very simple. It's an array of pixels, so you can feed that into input your first layer in a deep neural network. But text is more complicated. You could put an image of the text in, but the methodology that has striking performance currently is a method called word embeddings, where you take the text, you represent every text token as a feature in a space that is condensed, such that terms that have similar meanings will be co-located, coalesced into one single common element. And that feature space, when visualized here, I'm showing a graph of a word embedding space that was learned over a large amount of text. It's an unsupervised approach where you're looking at, the method looks at co-occurrences of terms to deduce similar meanings. This was a bunch of radiology reports, and you can see that terms that are related to each other tend to cluster together in that space. And that's a great representation because semantically related terms all are represented in the same feature, same value in the feature space. And that kind of representation, like in the deep learning with images, then can be used as your starting point for building a model. For example, an automatic information extractor or a classifier, you're going to feed in, instead of pixels in the case of images, you're going to feed in a word embedding representation of the raw text and then do your downstream AI task. And so with that as a background, I want to talk about the major applications that I see in radiology in particular, where you need both radiology images and text. The main ones, and there's a 36 or so FDA cleared AI algorithms as we speak. It actually increases every day. That may not be correct as of today, but that was what it was I saw as of 2 weeks ago. And almost all of those are focused on detecting disease, put an arrow down where is the disease, or making a diagnosis. And segmenting is used for measurement. So that is the current major thrust of the work in most of the publications. But actually, most of what clinicians need are the latter three bullets, which are treatment selection. What's the best treatment? That's the whole precision medicine paradigm. And that could be learned too using these deep learning methods. Response assessment, particularly in cancer. Is the cancer treatment working in that cancer as patients get longitudinal evaluations of their clinical and imaging data? And very importantly, clinical prediction. Will this patient, what's their survival outcome? When should they be switched from curative treatment to palliative treatment? Those are all predictive tasks. So I'm going to go through those pretty quickly and give you a few examples of work we've been involved with. So the detection and segmentation task is one of Where's Waldo? You're all familiar with Where's Waldo? So on this image, you look around and say, where is Waldo? And there's Waldo. Well, what the radiologist is confronted with an image like a chest x-ray, there's a similar Where's Waldo task that they need to do. Does anyone see the abnormality on the chest film? You can just raise your hand if you see it. Yeah, where is it? What is it? Yeah. So, and does anyone see the arrows on the image? So there's arrows on the image pointing at this area right there. That is a mass in the lung. Of course, the arrows didn't come out of the X-ray machine. Those are arrows added by the radiologist. But the task is that's the detection task. You'll find an abnormality in the image. And so there's a lot of methods that are being used. A lot of publications are using deep learning methods to find these kinds of abnormalities through training. And this was an example of work we've done to automatically detect and segment brain tumors. What's complicated in some modalities, like MRI, is there's multiple pulse sequences. And so you can't simply make a network and feed in all the images together. You'll need a network architecture that accommodates and takes into account the different appearances of lesions on different pulse sequences. So we have here 4 different pulse sequences that are typically acquired in MRI brain: Bravo, T1, T2 flare, et cetera. But it's a Google Net modified architecture, and the end result on the right is a map with an outline of there's a metastasis right there, which is automatically detected and segmented with excellent sensitivity and specificity, and a number of people are doing these kinds of projects. Another task is the diagnosis task. Okay, I've detected an abnormality, but is it cancer or is it something else? And that's the is it Waldo task. I mean, you found a Waldo, but it may not really be Waldo, it may be an atypical Waldo, maybe someone who looks like Waldo, but is really not Waldo. And the case in mammography is an example of that is it benign lesion or is it malignant lesion? So here are 2 masses, easy to detect. Question is it benign or malignant? And I'm showing you an example of a benign lesion, that's a lymph node, and a infiltrating cancer. And this is actually most of the value that radiologists currently add, is they can see subtle features that distinguish these two. To the untrained eye, you may not think there's too many differences, but there's a few subtle features that do distinguish these. Lymph nodes have a classic little indentation in them that looks like that. And infiltrating cancers tend to have a fuzzy margin and subtle spikes that stick out. And those are example features that radiologists pick up on. And so to show you an example of a deep learning approach to this, we and many other people are doing this. This is like one of the major applications people are using deep learning is to diagnose is it a cancer or not. We built a model that incorporates both views of the breast, CC and MLO, to parallel deep networks and final label diagnosis with very good predictive accuracy. And there's actually at least one commercial product that's FDA cleared for doing this now. We're actually taking that one step further. Some of imaging is real time. In other words, ultrasound, you're scanning, and you're moving the probe around. There's a lot of user variability in terms of do they see all the abnormalities, or endoscopy, a urologist who's putting a probe into the bladder and scanning around. You'd like to have an application that may help pinpoint where is the abnormality so they don't miss it, go by it. And that's really a single frame process. So I'm showing you, this is from endoscopy where a high resolution probe is put into the bladder. And this is what the physician sees. It's incredibly high resolution. This is pathology. It's a level of pathology. These are cells, these individual little round structures. The thing is, there's a lot of overlap in the appearance of cancer and inflammation and other diseases. And so we've been building deep learning models to real time predict what's normal, what's abnormal. Actually, if you can click on this frame here, we'll play the movie. These are the different diagnoses. This is normal, this is, great, yeah, just go ahead and click on that. And you can click on this one as well. So you can see that as they're scanning along, all of this is normal tissue, and as they're scanning in this case, in this region, all of this is high-grade cancer. So there's real-time feedback, and you can imagine, putting a visual overlay on top of those images to pinpoint, oh, this is the abnormality. That's really important to make sure people don't miss an abnormality or help pinpoint where should they do a biopsy to establish a final diagnosis. And the final clinical example I want to talk about, which I said is really important, is making predictions. And if you've got a lot of longitudinal data, you can make a prediction based on the clinical evolution of the signal and the data. And we built a deep learning model to predict patients who will survive more or less than 3 months who have metastatic cancer, with the goal being helping clinicians decide when should they start a discussion with the patient about switching to palliative care. And the model was using, now we're going to switch to using text, word embedding. So we take all of the clinical notes at each patient visit and build a word embedding model and make a prediction using a deep network built on the embedding of will they survive more or less than 3 months. But we train the model using all visits. So there's also connections between each of the visit models. And so this is an LSTM model that encompasses or incorporates time dimension. And the goal then is if the patient comes in, they have prior visits, then we can make a prediction at this time point, will they survive more or less than 3 months? And this is the performance of it. You can see the models perform incredibly well, more than 3 months survival versus less than 3 months survival, 0.89. And clinician accuracy of this is on the order of 0.7. We've done a similar model now incorporating image features. This was making prediction in age-related macular degeneration, which is an eye condition, a similar approach. But in this case, we want to predict, will the patient's disease progress over the next 3 months? And if it's going to progress, the patients are going to have treatment instituted early. And similar to the previous example, we compared, in this case, what if you build a model using random forest versus using the LSTM model? Huge difference in performance. So this shows the value of using longitudinal models for making predictions. I will end by talking about some of the challenges to building robust models. You need a lot of data to build models. This was a study that showed there's a lot of variation in the performance of models that are built on a data set, different data sets, and tested on other sites. So variability in performance, the robustness of models is a major challenge. And weak learning, you might have heard from Chris Ray earlier, is a new paradigm that is having great impact in medical image model work, where we learn weak labels, we learn from weakly labeled data with a paradigm called data programming. An example of that is, can we learn a model to distinguish normal and abnormal chest x-rays? And we labeled the models using data programming methods, took an NLP on the reports, coarse labels, and I'm showing you here how well the performance is in the case of 20,000, 2,000, 20,000, and 200,000 highly quality labeled cases versus poorly, weakly labeled cases. And the important thing to notice is that if you have 200,000 cases that are trained with quality labels, that's as good as you can possibly get. However, if you have 200,000 cases trained with weakly labeled data, noisy labels, so you took NLP of the reports and just ran a bunch of rules over it to make a prediction of the label, and then trained with all that, you start approaching the performance of that with a lot of quality label data. Another challenge is, how do we leverage data from many institutions? Institutions don't share data for many reasons. And so a paradigm of federated learning is emerging, where instead of bringing the data to the model, send the model out to the data. And so we've been developing methods for distributing the computation of federated learning paradigms to train these models in a distributed way. And this was a recent paper that we published where we compared different methods of doing the federated learning, and we found that by cyclically transferring the weights, this is where we take the data at institution 1, we fit the model locally, send the coefficients to institution 2, then 3, 4, and we cyclically do that many times. This is the performance with central hosting data. This is the performance of cyclical weight transfer. These were 2 other methods we approached. We can almost get the same performance of central hosting. I'm going to skip this slide, and final thing I'll just mention is, final thing that's a weak point is if you've got a robust model, the problem is if it encounters a case that's not within the distribution on which it was trained, it's going to fail. And how is a clinician going to know that? A good example is bone age. You can create a great model and recognize bone age and give a number. It'll be accurate. Test it on test data. Performs great. And what if it sees an elbow? It's going to give an answer. You might say that's a contrived example. But let's say you're doing a chest X-ray diagnosis and you have a whole bunch of pneumonias and other kinds of conditions, but you don't have too many examples of atelectasis. So if you encounter a case of atelectasis, then the algorithm's going to fail because it didn't have enough examples of atelectasis. That's an example of coming across a case that wasn't within the training distribution. And so we've been developing methods to detect out-of-distribution cases by incorporating into the training of the algorithm a confidence factor that it is going to learn not only the label, but how confident is the model that the case that it's looking at was within the distribution of cases that was used to train. And this is the performance of the ability to detect in distribution versus out of distribution. These are different types of images for the bone age. The clear one that's important, that's going to be in distribution, is going to be of the hand. And these are all the other kinds of images that a model may see and would give a fallacious result. And you can see by training this confidence factor, we do a really good job of separating cases in distribution versus out of distribution. And so the implementations would be when you deploy an AI algorithm, if it encounters a case that's not within its distribution, it would kind of say, no, I'm not going to give you an answer. That's not within my distribution of cases I was trained on. And that would give a clinician a warning, don't trust the output. It will probably be wrong. So in summary, the motivations is a lot of images, a lot of data. There's variation in practice, so we need computer help. Promising applications, I talked about a few in detecting disease, diagnosing, and clinical prediction. But there are some challenges related to having enough data to train a robust model, trying to bring data from many institutions together, and detecting out-of-distribution cases. And some of the techniques for overcoming these challenges are applying weak learning to leverage a large amount of unannotated data with weak labels, distributed computation or federated learning to tap into multi-institutional data without requiring data aggregation or sharing, and detecting out-of-distribution cases to alert the clinician if an algorithm might go off the rails. So with that, I thank you for your attention. Happy to answer questions.
Really like this presentation. Thank you very much. There was a statement that you made that bring the model to the data and not the data to the model. I didn't quite catch that. Could you please elaborate on that?
Yes. So in traditional machine learning settings, or most of them, if not all of them, when people build algorithms, whether it be companies to make a product or academics, you work with the data available. So the data is either public data, or it's in your institution, or you collaborate with a few institutions, but you bring that data into a single collection and you train a model. In the federated setting, you don't do that. You get collaborating institutions who hold on to their data, and you have each institution run an algorithm, training algorithm on their local data, and you share the weights. Now, there's different ways of doing that. You can do, I didn't have enough time because of time pressure, but there are different ways you can do it. The method we developed is called cyclical weight transfer, where you cyclically transfer the weight. So think about it as you train the model at one institution, you get coefficients, you send that to the next institution, you train using that as a pre-trained model, and cyclically move them around until convergence. There are other methods as well, but there were no data sharing. Now, I'll say there's potential security or privacy issues, because you could potentially, if you have small enough mini batches, the possibility of recreating the original data set. There are privacy things that we've been working on to avoid that problem, but there's no data sharing in this paradigm. And the results can be similar to the final result as if you aggregated the data. That's the point I was trying to make.